Y20 interference of light waves we have two light waves. They are monochromatic, the same lambda, same frequency, and there is a phase difference by phi. The resultant wave of these two is the same as a sine, an average value that has the phase difference from this by 1/2 of phi, and amplitude is 2 times A multiplied by cosine 1/2 of phi. You can see the shape of the resultant wave has the maximum amplitude at phi equals 0 and even multiple of pi. Or the resultant wave becomes a flat, that means it disappear when it is pi or odd multiples of pi. The maximum value for the amplitude. Amplitude is just absolute value of this one. And maximum amplitude is achieved when this one becomes a plus minus 1, and we know complete destructive interference, amplitude becomes 0, so resultant wave is 0. That is achieved when we multiply odd number to pi. The amplitude of the resultant wave for an arbitrary phase is actually the absolute value of this. The phase of the resultant wave for an arbitrary phase difference is, as is shown in here, 1/2 of phi. That is in the middle of these two waves. Electromagnetic wave propagating in space has two contributions. We have a wave that there is another wave with phase difference. The sum of these two lead to a resultant wave because there is a phase difference phi. The resultant phase is 1/2 of phi. The amplitude is 2 times cosine 1/2 of phi. Once the electric field is known, magnetic field is completely determined. As we can see in here, this wave propagates along the z-axis. Because it is a minus, it is propagating along the positive z-axis. We have the electric field in here that is along the x-axis. Then, according to Maxwell's equation, especially from Gauss' law in vacuum, this one shows that electric field and magnetic fields are perpendicular to the wave vector, and we have Faraday's law. According to this, we can see E field, B field, x-axis, y-axis, and wave vector k, they construct x, y, z-axis. So magnetic field multiplied by c, you must not miss this. C must be multiplied to have the same dimension, same amplitude. So it is along the x-axis, y-axis, and wave is propagating along the z-axis. So magnetic field is completely determined from this, or it is equivalent to use Maxwell's law. Maxwell's law of displacement current. Okay. Resultant electromagnetic energy density is this one and this one, sum. And in here, we multiplied C, then we divide it by C squared, and we have mu 0, factor of 2. And C squared is mu 0, epsilon 0 in the numerator. Mu 0 cancel. Therefore, we have the same factor. And E squared plus CB squared. Square, square. Sum them all. The final result will be like that. And if you have a space-time average of the resultant wave, this is a constant. You have to average over either space or time. It is just 1/2. So factor of 4 become factor of 2. And actually, electromagnetic field energy density is this. And if we multiply the speed of light, then you will obtain the magnitude of Poynting vector. That represents the flux, the energy current density of the electromagnetic field propagating in space. Next, we consider interference of two waves. They are monochromatic. They are of the same amplitude. However, here it is going forward along the x-axis. Here we have positive sign represents that phi 2 propagates in opposite direction, minus E1. The two waves are making a head-on collision. So head-on collision is this situation. With the relative velocity, it has a velocity v that is omega over k, and it has a velocity minus v. So relative velocity is 2 times. If it is seen from 1, it is a minus 2v. It is seen from 2, its relative velocity is 2v. The sign depends on the who, depends on whom, who is observing the situation. The spatial factor and the time-dependent factor are completely factored in resultant way. Yes. Cosine, because of this negative sign, plus sine. Cosine, because it is plus, we have negative sign, sine. They cancel. So it becomes the double, and the kx and omega t, these two factors are completely factored. So we can write it as a cosine omega t and cosine kx. In space, x-axis, we have lambda, if we choose this one to be origin, this kind of shape. And if we consider time-dependent factor, you can observe these nodes and antinodes. The positions of nodes and antinodes doesn't change. So it is oscillating at the same place. Stand up, stand down, sit down, stand up, sit down, stand up. So it is a standing wave. It doesn't propagate. Propagation from the left to the right, propagation from the right to the left, because of the head-on collision, the flux to the right, the flux to the left, they cancel. Instead, they are fluctuating at the same place. Because this function is not of the form kx minus vt, it is just the f of x times the g of t. Spatial part and time-dependent part are completely factorized. Distance between any two adjacent nodes or antinodes is 1/2 of the wavelength. Yes, this is the wavelength, and this is 1/2 of the wavelength. Okay. We have a single wave propagating on 2 dimensions. We introduce 2 sources, 2 coherent sources. They oscillate with the same frequency and their wavelengths are identical to each other. Then you can find there are concentric rings. The distance between these two determine the wavelength. However, if there are 2, the shape, even though we cannot identify the 2 sources exactly, but you can see the amplitude at this point and this point. This fluctuation looks a little bit different. And as we increase the distance d between the 2 sources, you can see the fringes. If it is a light wave, these fringes will be dark and bright points, and this is a dark points, and these are bright points. If it is in a ripple tank, it is just a wave. And as we increase the distance between the 2 wave sources, the fringes become very dense. Let's see. 4D is not equal to 0. one can observe destructive interference pattern. These are destructive interference, and these are constructive interference, something like that. The fringes of destructive interference pattern become narrower as D increases. Yes, the pattern change. It seems that there is a constructive and destructive. The scale becomes narrower and narrower, and you can see the gap between the two nearest destructive interference points or constructive interference points. They look very busy. So we say as we decrease the distance between the two sources, the interference pattern of the two waves become magnified. So from here to there, we can see the diffractive behavior. The angular distance between two nearest points of the same interference pattern grows larger as this one decreases. So when D becomes smaller for a fixed wavelength lambda. Delta L, that is the path length difference, is a multiple of the wavelengths. In that case, we have constructive interference that we learned from the standing wave in one dimension. And if we have half integers, that is equivalent to 2 pi. Therefore, multiplication of a half integer is equivalent to multiply odd number to pi. In that case, we have destructive interference. If you carry out a little bit algebra, you will find the equation for the points that has a fully constructive interference or fully destructive interference. The reason is that this is a trajectory of a hyperbola. I don't know whether you learned how to, do you know what it is? Do you know what it is? This is a circle. This is an ellipse. It is very similar to that, except that we have negative sign on it. This is hyperbola. The equation of hyperbola has a geometric meaning that the track, this trajectory of this curve represents the points we have distance 1, distance 2. This is a point P, and these are point sources, source 1, source 2. This D1 and D2 determines the point where sine kx minus omega t fluctuates. So if D1 changes by D1 plus lambda, then these 2 points are of equal phase. Therefore, D1 and D2, if we subtract and find the difference between the two, then you will determine the point at which the fully constructive or fully destructive interference. Okay? So if the D1 minus D2 is absolute value of this is n lambda, what happens? These points will be a constructive interference. If D1 minus D2 equals a half integer multiplied by the wavelength, then it becomes the destructive interference. Okay, that's the reason why there are many curves. Some of them is constructive interference, some of them is destructive interference. Okay, among them, we choose a single one. You will find this one has a special track. What does it mean, this A? Here source S1, source S2, and there are curves. This distance, this is because of symmetry, these two are the same. For example, let me choose this point. Then D1 is this, and D2 is this. And we know these two are the same. So D2 minus D1, absolute value, is nothing but this distance, that is capital A. Aha, capital A represents the distance difference. If capital A is multiples of the wavelength, then this curve represents the track of points of constructive interference. If it is an n plus 1/2, half integer, multiplied by the wavelength, then this A represents this, then it is destructive interference. All right. And you can make simple algebra just to square this one and simplify this expression. You end up with this. And all of these are conic sections. Conic section is cross section of a cone. If you cut a cone by using a plane that is parallel to the base, it is a circle. If you give some angle, then it becomes ellipse. If you increase to have the angle parallel to this line, then this trajectory is hyperbola, a parabola. And if you cut it vertically, then you will get a curve that is shown in here that is called hyperbola. And actually, among these, all of the circle, ellipse, parabola, and hyperbola, Kepler found the track of celestial bodies under gravitational force. The Kepler's planetary motion's first law is called the law of ellipse. And in the first semester, probably you have not learned from me, any celestial body under gravitational force, if it is simplified into a two-body problem, it is one of the four. The orbit is just one of the four cases. Okay. As you can see, when we increase the distance between the two sources, the number of curves increases. It becomes very busy. So angular separation becomes very dense when you increase the distance between the two sources, keeping the wavelengths the same. This is due to the diffractive behavior of light wave. Trajectory of equal path length difference is a parabola. Really? It's a hyperbola. The central constructive interference pattern is always the central constructive interference pattern is always placed along the symmetry axis, the central straight line. Path length difference must be less than d. Red bands are constructive interference trajectories. Blue bands are red maximized, amplitude maximized. Blue becomes a smaller. Blue one shows the interference trajectory for the destructive interference. Number of parabola, no, hyperbola. Seven, the left figure shows a single point. The figure in the middle shows the resultant wave of n equals 10 coherent waves, many waves, equally distributed in an aperture with A equals lambda. So there are 10 sources. Okay. Can you distinguish the resultant waves? It is a symmetric. There are nodes and antinodes. If we increase to 100, this is the demonstration of Huygens Principle. If you collect many coherent sources all together as a series, then you can generate a plane wave. However, you can see at the edge, this wave is circular. At the center, it looks like plane wave. However, if you go farther and farther, then you will find even this plane wave source coming out of a hole. If you go very far, it becomes spherical wave. Or on a plane, it is circular wave. It looks plane wave right in front of a hole, but if you go travel further, it becomes circular wave. This is a Huygens principle. Okay. These are examples of what we have discussed until now. You will find as d increases by fixing the wavelength lambda to be the same, you will find many number of fringes. This is a demonstration of Young's experiment for the two-slit experiment. And the screen, if you put some screen from a certain distance, capture D, and if it is a screen, then you will find fringes, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. Okay? If you assume the capital D is very large in comparison with the distance between the two slits, the source of two waves, then the distance D can be interpreted as this one, and these 2 points represent the same position. Source and a point P on a screen, even though I draw a triangle, if it is very far, this part can be drawn like that. An actual phase, a path difference between the two lights from the two sources can be expressed like that. The angle theta, this is S1 and S2. This angle, theta 1 and theta 2, and this angle, theta 1, they can be treated to be the same. And that angle, this angle, is identical to this angle. Because the separation of the two slits is a small d, the path length difference is a d sine theta. Using that relation, we can find the point at which the constructive interference appears and destructive interference appears. The relations are identical to each other. Substituting these electric fields coming from the two sources, we can carry out some algebra. Again, the resultant wave has a typical shape of interference. And in here, we can find this phi depends on the phase difference. Phase difference. This path length difference divided by wavelength. Okay. Again, we can consider the brightness is related to the electromagnetic energy density deposit on that point. Using this, in the next lecture, we study further about the details about the interference pattern of the diffractive light wave.